Good morning, boys and girls. It is Monday. It is June 8th, and I'm going to do a quick review of the theory of seafloor spreading. And in order to do that, I'm going to take us back to the slide where I asked you to imagine if you could see the landscape at the bottom of the Atlantic Ocean from Rhode Island in North America all the way across the North Atlantic to Europe. What might it look like? And when I looked at many of your answers, many of you answered very similarly. Many of you said there would probably be some rocks. Many of you said there would be very sandy. And not very many really actually knew what the bottom of the ocean floor looked like. And that did not surprise me because until we started to use echo sounding or sonar to map what the bottom of the ocean looked like, most scientists believed pretty similarly that it was flat and void of any unique landscape. That all was turned around, though, for us in the 1950s when this gentleman to the left named Bruce Heezen and this lady, Mary Tharp, to the right, actually teamed up in scientific investigation of the bottom of the ocean floor. Now, Bruce Heezen was a geologist, and that really is a scientist who studies the solid earth and the interior of the earth. So he was a geologist by profession, but he was also in World War II. And in World War II, he was a Navy captain. And one of the things that he did is use sonar to take depth measurements of the ocean floor. Now, he and Mary Tharp joined forces to map the ocean floor. Now, poor Mary, she was as bright as Bruce Heezen himself. She too was a geologist. She had many degrees in other areas, but she was not allowed to go out on scientific expeditions because in the 50s, boys and girls, women were considered subservient or below men, and they thought that it might be bad luck if she was allowed out on the ships. So Mary was told she could not go on the ships, and she stayed back in her office. And what she did, though, is she took all of the measurements that Bruce Heezen and his male partners took of depth of the ocean floor, and she converted that data, all of those numbers, all of that quantitative data, she converted it into line graphs, and she connected all of the line graphs and the dots and created the first map of the ocean floor. And her big discovery was that the ocean floor is not flat at all. Instead, it is full of a plethora of different landscapes and different features. There are plains in the ocean floor, flat areas certainly that most people thought. We call those abyssal plains. Abyssal means deep in ocean. But there are also mid-oceanic ridges. There are underwater seamounts. Seamounts are just volcanoes that are still underwater, and the individual volcanoes, unlike the mid-oceanic ridges, which are underwater volcanic mountain ranges. There are also other different features as well, and through her using the data to create a model of the seafloor, this was discovered. And you can see here in this picture that I have of Marie Tharp when she was much younger. This is actually a picture of her drawing the bottom of that looks like the Indian Ocean to me. And you can see to the left in the picture of her is one of her line graphs of the data that shows the different depth measurements and actually how you can actually start to see the different features of the ocean floor. She was responsible for discovering not only the Mid-Atlantic Ridge, but the rift in the center of the Mid-Atlantic Ridge. And the rift is just this big crack in the center where seafloor is being created. And she was the first one to suggest that to Bruce Heezen, because through further study of her maps that she created of the features, she compared them to other maps of the ocean floor and saw that earthquake location actually corresponded to her maps of the Mid-Atlantic Ridge, and she inferred that there's something happening down there. Not everyone believed Marie Thorpe right away because she was a woman, but eventually Marie and Bruce came up with this whole idea of there's something happening down there. And it was certainly Harry Hess that put together what Bruce Heason and Mary Thorpe did to create the idea of seafloor spreading, which I'm going to go on to in just a few moments. Before I do, let's take a look. This is actually Marie Thorpe's first map you're looking at right now. And what we can see that really is significant, that sticks out, is in yellow are the continents. And we can clearly see that those mark the continents. In blue is the ocean floor. And we see these features. They almost look like alligator or crocodile backs snaking through the world's oceans. Boys and girls, those are mid-oceanic ridges. The two that are most studied by scientists are the Mid-Atlantic Ridge, which runs down about 10,000 miles right through the whole Atlantic Ocean. It snakes through the Atlantic Ocean, and that's why it's called the Mid-Atlantic Ridge. And the other ridge that's really studied is called the East Pacific Rise. Now, it's right here. I'm highlighting the East Pacific Rise. It's located in the East Pacific Ocean, and it is a ridge, just like the Mid-Atlantic Ridge, but it's called a rise, and this is just a fun little fact. It's called a rise because this ridge is not as tall as all the other ridges, and the reason for that is it has a spreading rate much faster than the Mid-Atlantic Ridge and some of the other ridges. So the tops of these mountains don't get as steep because it just keeps on pumping out lots of new oceanic crust right there. So here's Marie Thorpe's first map of the ocean floor. Pretty wild. Our ocean floor is not completely flat. Certainly there are flat areas, but our ocean floor has ridges in it. It has some underwater individual volcanoes, and also has these features called deep oceanic trenches, which I'm going to talk about in this slideshow very shortly. This is another map that was put out by National Geographic of Marie Thorpe's findings, and this really pronounces those mid-oceanic ridges. So you really get a sense of what the bottom of the seafloor looks like. It is pretty wild. So everything that is on the continental crust, all of the land features, mountains, plains, crevices, volcanoes, you name it, whatever we find on the continental crust is also found deep below the world's oceans on the oceanic crust. Now, here's a fun fact. The mid-oceanic ridges are the longest mountain range on Earth's surface. They extend about 65,000 kilometers around the globe. That's equal to 40,000 miles. And they're often described as being like seams of a baseball. So in the upper picture here, in the upper right, you can see the Mid-Atlantic Ridge here, and the rest of the ridges, they actually are drawn to depict almost like seams like a baseball. Now, what's really important, kids, is those ridges are all connected. And you can see here's the Mid-Atlantic Ridge that we've highlighted, and then they connect all through the world's oceans, these giant cracks in the lithosphere of planet Earth. And these mid-ocean ridges are areas where new seafloor is being created. Now, here's a nice little video of a tour of the ocean floor. And you can see this tour will actually suck the water out of planet Earth and give you a nice little view of what it looks like down there. Okay, this is really wild. So it's just as diverse the landscape as the continental crust. We have high areas, we have low areas. Coming from a continent, we can see that the continent is higher than the ocean floor. It sinks down. We have these great big mid-oceanic ridges, which are underwater volcanic mountain ranges that wrap around the globe. The length of the mid-oceanic ridges, again, about 40,000 kilometers around the world. There's that East Pacific rise again in the East Pacific. It has about a 14 centimeters per year of a spreading rate. In comparison, very quickly, the Mid-Atlantic Ridge is just about 2 centimeters per year. That's where the Titanic is located in the North Atlantic, about 3.8 kilometers down. There is Iceland in the middle of the North Atlantic. And here's another interesting fact. Iceland is actually born from the Mid-Atlantic Ridge. So it's right on top of the Mid-Atlantic Ridge. That's just a really cool tour. And I'm going to upload this onto Google Classroom for your enjoyment so that you can check it out. It's very neat. So now, big vocabulary in this whole idea of seafloor spreading are mid-ocean ridges is the first vocabulary. Those are just undersea volcanic mountains where new ocean floor is being created. And again, they look like those big giant alligators or crocodiles or reptiles running through the bottom of the seafloor. Those are volcanic mountain ranges. And in the center of mid-ocean ridges are these giant cracks we call rift valleys. Rift is a fancy word for crack in the crust, guys, and it is that rift valley where lava oozes up from the mantle, and that's where the new rock is being formed. So how does the process work? The process of seafloor spreading simply is the process where magma from the mantle rises through that rift valley in the center of the ocean, of the mid-ocean ridges. It creates new ocean crust. Now, guys, over time, as more and more new oceanic crust is created, it pushes the older ocean crust outward, and the seafloor spreads over time. This animation is really good at showing you how the process works. Now, this animation is definitely different than the real model. This animation is showing this in conveyor belt style, fast forward very quickly. This process ever so slowly. Most mid-oceanic ridges are creating new crust at about 2 centimeters per year. So the process is very slow. You can't even see it working. The process is about as quick as your fingernails grow. Now, I've used that before, and I've used that analogy before when I talked about tectonic plates. Tectonic plates move at about 2 centimeters per year as well. And boys and girls, convection currents in the asthenosphere move about 2 centimeters per year. So there's no coincidence that all of this is about 2 centimeters per year. Convection moves at about 2 centimeters per year. The seafloor moves at about 2 centimeters per year. The tectonic plates move about 2 centimeters per year. And the reason why this is not coincidental is they all are related. So convection currents in the asthenosphere is really what's driving the process of seafloor spreading. So new seafloor is being created, yes, and old seafloor is being pushed away from the mid-oceanic ridges. But what's the force to help that motion? It's convection underneath in the asthenosphere. The other significant feature in the understanding of seafloor spreading would be deep ocean trenches. Now, deep ocean trenches are land features at the bottom of the ocean floor as well. Let's take a look at the picture in the upper right-hand corner. This is a small section of, this right here would be the Baja Peninsula of California. And when we look at maps of the ocean floor, we see these darkened, deep, almost like crevices. Those are mid-ocean, those are deep sea trenches. And here's another trench here, which actually runs down the whole entire length of the west coast of South America. Now, trenches are these deep valleys along the ocean floor, and they're very significant because this is where older, colder, and denser crust slowly sinks back into the mantle and is recycled. So we have mid-oceanic ridges where new seafloor is being created. We have deep sea trenches where old oceanic crust is recycled. So we need to remember that. Ocean ridges and trenches, two significant land features in our understanding of seafloor spreading. Now, that whole idea of recycling back into the mantle is called subduction. Think of that word sub, that prefix. Sub means to go under. So subduction is the process where older, colder, and denser ocean floor sinks back into the mantle via the ocean trench. And this is a terrific animation showing you the process, but showing you the process speeded up because, again, it's about 2 centimeters per year. So it's very, very slow because, again, convection currents are what dragging this old oceanic crust back into the trench. So when we look at the animation, right where my cursor is right now would be where the deep sea trench is, and this would be all the ocean floor being recycled back into the mantle. So here's a fun fact. When we look at this picture, I have placed arrows everywhere where there are trenches on our planet. There's actually trenches here in the South Pacific that I have forgotten to label. Most of the world's trenches are actually in the Pacific Ocean. The Atlantic Ocean just has two small trenches. But here's a fun fact. The trenches are the deepest places in the world, and the Mariana Trench is the world's deepest. You might have heard about the Mariana Trench before watching Finding Nemo. I think the little fish that goes down there goes down to the Mariana Trench. I have labeled the Mariana Trench with the star on the map. It's this crescent trench that I'm actually highlighting with my cursor right now. It is almost 7 miles deep, boys and girls. That means if I cut the Himalaya mountain, what's the tallest one there? The Mount Everest. Sorry, it eluded my my brain for a moment. If I cut Mount Everest from the base and threw it into the trench, do you know that the Mariana Trench would swallow Mount Everest whole? It is deeper than Mount Everest is tall. It's 36,201 feet deep to be exact. So now here is a nice picture of the world's trenches and ridges. Trenches are highlighted in red, ridges are highlighted in green. So trenches and ridges are giant cracks in the Earth's lithosphere. Ridges are sections where new oceanic crust is being created. Trenches are places where old oceanic crust is being recycled. Trenches recycle ocean crust in a process called subduction. Ridges create new oceanic crust in a process called seafloor spreading. So everywhere you see a green line, new seafloor is being created. Those are mid-oceanic ridges. Everywhere you see a red line, those are deep sea trenches, and this is where old oceanic crust is being recycled. Now, who's the guy who proposed the idea of seafloor spreading? Well, it was Harry Hess, this gentleman you're looking at right now. Harry Hess took Bruce Heezen and Mary Thorpe's discoveries and maps of the ocean floor, and he put it all together, and he is the scientist who is given credit for proposing the theory of seafloor spreading in the early 60s. What does his theory say? Well, it says exactly what I just reviewed, that the seafloor spreads when magma from the mantle rises through the Rift Valley in the center of mid-oceanic ridges, creates new ocean crust, and pushes the old crust away from the ridge. Huge discovery. Now, how does it all work? So if we look at this picture and how I've labeled it, 5 simple steps, I've really tried to condense the understanding. Step 1, magma rises through the Rift Valley in the center of the mid-oceanic ridges. That magma now becomes lava because now it's on the surface of the ocean floor. It cools, and when it cools, it forms rock on either side of the ridge, which is depicted by, say, these red arrows. Step 3, as more seafloor is created, the older seafloor is pushed away from the ridge, and what happens? It spreads the seafloor. The seafloor gets bigger. Step 4, the older and colder seafloor, which is much denser, guys. Cold is more dense than hot, okay? It sinks into the ocean trenches. And at the bottom of the trenches for step 5, the old seafloor is recycled back into the asthenosphere. It gets pushed in the mantle where it melts, and that is called subduction. So we have magma rising in the center of the mid-oceanic ridges, cooling, forming new rock. That new rock pushes the old rock away. That old rock eventually sinks into deep oceanic trenches and is recycled into a process called subduction. Now, what drives all of this? Again, let's do a quick review of convection. Remember, convection is heating, rising, cooling, sinking of fluids. We believe that convection in the asthenosphere is moving the seafloor and drives that whole process of subduction. So this is a terrific animation in the lower right-hand corner of your screen of the process. As the convection currents move in the mantle, they drives the lithosphere that sits on top, and it's actually what's moving the seafloor apart at the rift valleys and mid-oceanic ridges, and what's actually bringing the old seafloor to the trenches and recycling the seafloor. Now, like any good theory, you need evidence to support it. Harry Hess needed evidence, and he went out and sought out the evidence. Now, you've read about 3 pieces of evidence to support this idea. I'm going to highlight 2 important pieces, not 3. The first piece of evidence I'm going to highlight comes from molten material we call pillow lava. Now, take a look at this video I'm going to have playing right now. Let me mute it. When you take a look at that video, that's actually lava that's erupting on the sea floor. And check it out, how it cools from the outside in. So we get this thin crust being created right on the outside surface of the lava, guys, which actually creates almost like a tube that the hot lava can flow through. And what ends up being the result once the lava flow ends and completely cools is this hardened lava formation we call pillow rock. So in the lower left-hand corner of your screen, you can see there's a picture of pillow lava rock formations. They're called pillow lava rock because scientists say that these rock formations look like giant pillows sitting on top of each other. What you're looking at, boys and girls, is brand new basaltic rock along the mid-oceanic ridges. So when scientists get down there in their submersibles, you can see that there's looks like there's these mechanical arms in this picture in the bottom. Those mechanical arms come from a deep sea submarine called Alvin. I'll show you a picture of Alvin in 2 seconds. When scientists take submersibles down to the mid-oceanic ridges, this is what they see at the Rift Valley, these pillow lava rock formations of basalt. Now, what's so significant about pillow lava and how it supports the theory of seafloor spreading? Well, pillow lava, guys, only forms when lava cools underwater. The fact that these rock formations dot oceanic ridges proves that lava is being pumped up from the ridges. Huge, significant piece of evidence to support the idea that new oceanic rock is being created. So this is the first piece of evidence I'm going to highlight, evidence from molten material we call pillow lava. Here's a picture of Alvin, the submarine used to observe mid-oceanic ridges. It actually can fit 2 people. I don't know about you, but I would be hugely claustrophobic in there. Wicked cool, however, and that's what this submarine scientist is still using today. They started using Alvin in the 50s, and they're still using Alvin to investigate deep sea oceanic ridges. The second piece of evidence, which is very significant, almost seals the deal, comes from age evidence from drilling samples, drilling rock samples. The age of the ocean floor, boys and girls. Sorry, you can hear my phone ringing in the background, but I am not going to stop my lecture right now. So the second piece of evidence comes from age evidence from drilling rock samples. And so scientists are able to drill into the ocean floor. They drill using these deep sea drilling ships. One was called the Glomar Challenger. And what they have found is that young rocks are found closer to mid-oceanic ridges, and older rocks are found further away from the ridges, most often near trenches or the edges of continents. Now, this picture in the lower left-hand corner is really a nice map of the age of the seafloor crust. You can see it's color-coded. Here is a better map. So let's just kind of make sense of what we're looking at. In gray are highlighted the continents. The continents are highlighted in gray. Here is North America, here's South America, here's Africa, Europe, Asia. In the different colors, rainbow colors, that's the bottom of the ocean floor. And the different colors indicate the different age of the ocean floor. At the bottom of the screen would be the key. Red indicates rock that is very, very young. And as the colors change, we get to blue, which indicates the oldest seafloor rock at about 180 million years. So the age of rock is dated in millions of years. So we see red rock is found right along those cracks in the deep sea floor. Those are the mid-oceanic ridges. Everywhere you see red, boys and girls, are the mid-oceanic ridges. That's new, young oceanic rock. And as we move further away from the ridges, the seafloor age increases, with the oldest being found along continental edges or near trenches. This right here where my cursor is right now, that's the location of the Mariana Trench. You can see the age of the rock is blue, which is old. So we have this age evidence that also proves that rock is being created at different times in geologic history, and new rock is created along these cracks in the ocean floor that are mid-oceanic ridges, those underwater volcanic mountains where new seafloor is being created. So now here's a big question. If new seafloor is always created at the ridges, then why isn't the Earth getting bigger and bigger and bigger, like blowing up like a balloon, all right? I'm telling you, the seafloor is constantly created at the ridges. Well, the answer is, as new seafloor is being created one place, old seafloor is being recycled at the trenches. So the Earth itself, boys and girls, the land, the seafloor, is able to keep at an equilibrium. As new seafloor is being created, the same amount of old seafloor is being recycled. And this would explain why the Atlantic Ocean is increasing in size and the Pacific Ocean is decreasing in size. Let's take a look at the Atlantic Ocean. It is marked by the mid-Atlantic ridge that runs right through the center. That's where new oceanic floor is being created. The Pacific Ocean, if we look at the Pacific Ocean has more trenches in it than it has ridges. The Pacific Ocean's trenches are gobbling up the Pacific Ocean floor faster than the oceanic ridges that are in the Pacific can create new ocean floor. So the Pacific Ocean is shrinking in size because it has more trenches than it has ridges. The Atlantic Ocean is increasing in size because it has more ridges than trenches. It just has these tiny two little trenches. It can't gobble up ocean floor fast enough to reduce the size of the Atlantic. So the Atlantic is growing and the Pacific is decreasing. So again, seafloor spreading says the seafloor spreads when magma from the mantle rises through the Rift Valley in the center of mid-oceanic ridges, creating new oceanic crust and pushing old crust away from the ridge. Now, what's so important about this? What did this theory of seafloor spreading do for geology? Well, it did something about explaining about continental drift. Let's take a look at the big idea here. Seafloor spreading actually helped to explain how the continents moved. Remember, Alfred Wegener didn't know the how and the why. So Alfred Wegener died in 1930. He proposed his idea of continental drift in 1912. Here comes 1960, 30 years after Alfred Wegener died, almost 50 years after he proposed his theory, we have the how the continents are moving. The continents are moving because as the seafloor spreads, it pushes the continents with it. So let's take a look at this animation. So when the animation starts, picture, if you will, Pangea. And as the animation continues, what we have is Pangea breaking apart because of the birth of the ridge. The ridge is born and cracks the continents in different pieces. As the ridge gets bigger, it pushes those continents further away. And boys and girls, the ridges are still pushing the continents farther and farther apart. So, what pattern do you notice about the outline shape of the mid-Atlantic ridge in the continents? Let's take a look. I'm going to outline the entire mid-Atlantic ridge here. When I outline the ridge, when you look at that ridge and compare it to the outlines of the continents on either side of the entire Atlantic Ocean, you should notice something. And you should notice that the outline of the mid-Atlantic ridge is the same shape as the shoreline of the continents. That is not coincidental. It is the same shape because it's the mid-Atlantic ridge that actually split up those continents. So if we could go backwards in time to the time of Pangea, the mid-Atlantic ridge would be the boundary between South America and Africa when those two were connected. It would also be the boundary between North America and Europe when those were connected. This brings us to the main idea here. What similarity do you observe between the ridges and trenches and the tectonic plates? So in the upper left-hand corner, this is a map of the ridges and the trenches of the world, boys and girls, outlined again, the ridges in green and the trenches in red. When we compare this map to the map of the world's, the Earth's tectonic plates, you should see that they are very similar. In fact, it's the ridges and the trenches. They mark the boundaries between the different tectonic plates. They are tectonic plate boundaries. The mid-Atlantic ridge that I'm highlighting right now in the upper left-hand corner map, the mid-Atlantic ridge is actually the boundary between four different tectonic plates. We're going to move forward today and learn a little bit about that whole idea of plate tectonics, because remember, that theory states that the Earth's lithosphere is broken into those tectonic plates. Those tectonic plates are actually trenches and ridges, and those tectonic plates move all over the Earth's surface because of convection in the mantle. And the whole idea of the plate tectonics actually is the combination of continental drift and seafloor spreading. You take those two theories and it actually creates the theory of, or they actually create the theory of plate tectonics. So here's a picture of Earth's tectonic plates, boys and girls, and you can see it's riddled with arrows. The arrows actually tell you what's happening at those plate boundaries. Because remember, tectonic plates are not stagnant. They move. They're moving ever so slowly at a rate of about 2 centimeters average per year. So there's three different ways that boundaries can move or interact. Those three different ways are, they can come together. So when we see arrows with facing each other, That's called a convergent boundary. They can spread apart. When you see arrows that are moving away from each other, that's called a divergent boundary. That's actually mid-oceanic ridges are divergent boundaries. And the third way that they can interact would be they can move past each other, and those are called transform boundaries. So when we look at a tectonic map, we're going to be looking at arrows to determine what's happening between the different tectonic plates at those boundaries. Today, you're going to investigate a tectonic map and investigate the different boundaries, because those boundaries are very important, and they determine the type of land feature that is created on the Earth's surface. So the tectonic plates, their motion and their interaction create different land features on our surface. They also trigger different geologic hazards like earthquakes and volcanic eruptions. So for today through Wednesday, boys and girls, to try and condense our big unit of plate tectonics, I'd like you to investigate what happens at plate tectonic boundaries, the land features that are created, and the geologic hazards that are also created because of that.